Okay, so today we're going to learn how to find the volume of the solid of revolution. And in this first part, we're just going to learn how to find all the necessary information that we need to find that volume. So first, let's talk about what a solid of revolution is. So let's say I have the region enclosed here in red that is enclosed by the graph of y equals sine x on the top and y equals 0 on the bottom. And I want to take that region and I want to rotate it around the x-axis here to form a shape. So let's kind of get an idea what that would look like. So it's the same thing. As you see, as this curve gets rotated around, creates almost this football-like shape that we have right here. And you can see that. I'll take this and I'll drag it around a little bit. You can see that it's a three-dimensional shape. All we did was rotate that region around. We have this solid of revolution. So what we're going to do is we're going to take this and we're going to find the volume of it once we find some necessary information. And one way we're going to do that is we're going to divide this thing up into small washers. And washers, if you've seen like you ever put, screw something together, build a piece of furniture or anything like that, you get the little washers that kind of look like a circle with a hole in it. That's the kind of shapes that we're going to end up finding the volume of. And sometimes they'll have a hole in the middle, sometimes they won't. In this case, we won't actually have a hole. If you think about when we rotate this around, there'll be no gap inside because of this side being attached to the region, but we'll talk more about that in a minute. But we're going to take one of these things, rotate it around, and we will find the volume of that. And then we'll do that infinitely many times over the width of this region to the point where we get something like this. We'll take all these, the volume of all these washers together, add them up, and that will tell us the exact volume of that solid. So first, let's get some necessary information and decide what we need to find out. Well, what do we need to know? First, we need to know the lower bound. And the lower bound will be the lowest x value contained in the region, since we're rotating around the horizontal axis. Second thing we're going to need to know is the upper bound. The upper bound will be the highest x value contained in the region. Third thing we're going to want to know is the radius of the outside circle. Like I said, we're going to have a washer, and we're going to need to find the volume of that little washer. So we're going to need to know the area of the base and the height. And to find that area of the base, we're going to need to know the radius of the outside circle, which will denote big R. That's the distance from the outside of the region to the axis of revolution. And then we're going to need to know the radius of the inside of that thing to figure out what part we need to get rid of. And that's we're going to denote with a lowercase r. And that's going to be the distance from the inside of the region to the axis of revolution. So let's look at an example. So we're going to use this graph and we're going to find all the necessary information needed to find the volume of the solid created when we rotate it. But first, let's get an idea of what that looks like. So see, as we start to rotate this thing, we kind of get this thing that almost looks like a trash can lid. Okay, so that's the thing we're finding the volume of. Okay, so what's going to be the lower bound? Well, the lower bound is the lowest x value of the region. So as we look to the left, okay, the lowest x value we see that's actually contained in this region is 0. So that's going to be our lower bound, 0. Next thing we're going to find is the upper bound. So the upper bound is going to be the greatest x value that's contained in the region. So as we're going across our region here, we see that it kind of stops here at x equals 2. So that's going to be our upper bound, 2. Next thing we want to do is find the radius of the outside of the circle. And that's going to be the distance from the axis of revolution out to the outside of the shaded region. So I'm looking at that distance, and I'm looking where I stop on the shaded region, that's right here. And notice that regardless of where I slide this thing, even if I draw it out here, the outside part is always going to be, it's a little crooked, but it should be a straight line. The outside of that region is always going to be the graph of y equals 4 minus x squared. So we're going to say that the radius of the outside circle is going to be r equals 4 minus x squared, because that's always going to be the outside of this region no matter where we're trying to find that that width of that shape. And then lastly, we want the radius of the inside of the circle, which, since in this case the shaded region is actually attached to the axis of revolution, the distance between the axis of revolution and the inside of the shape is going to be 0 because it's actually the same line. So the radius of our inside of our circle, little r, is going to be 0. So for this one, lower bound 0 because it's the lowest x value, upper bound 2 because it's the biggest x value that's contained in the region, radius of the outside of the circle, we go to the outside of the shape, measuring the distance from the axis of revolution, that's always going to be 4 minus x squared, and the radius of the inside of the circle, since the axis of revolution is attached to it, it's going to be r equals 0. Let's look at another one. So we have the graph of y equals 1 minus x to the third plus 1 on top here, and that's bounded on the bottom by y equals 1. And it's going from x equals 0 to x equals 1. So let's get an idea what that shape will look like. So we'll pull this up here, and you can kind of view how it generates the solid. So kind of goes up. Notice we have this hole in the middle. Okay, so we have a true washer. It kind of looks almost like a button on your jeans or something like that. So we're going to find that necessary information again. So we look at the lower bound. What's the lowest x value or the leftmost x value that's actually in the region? Well, that would be x equals 0 because you see that the shaded region doesn't go past x equals 0. So our lower bound is 0. Our upper bound, well, once again, we're going from the axis of revolution out to the outside of the shaded region. Okay, and no matter where I draw this line, the outside of that region is always going to be the graph of y equals 1 minus x cubed plus 1. So that's going to be our big R. So big R equals 1 minus x to the third plus 1. Okay, we skipped over the upper bound for a minute. So what's the greatest x value that we have, or the one that's furthest to the right? And that would be x equals 1, so that'll be our upper bound. I apologize for skipping over that for a minute. And then we want to find the radius of the inside of that circle. Well, that's going to be the distance from the axis of revolution to the inside of the region. So now I touch the inside of the region. No matter where I drag that region inside here, I'm always touching that graph y equals 1. So my radius of the inside of the region, the inside of that washer that we're going to end up rotating, it's going to be little r equals 1. And so go ahead and do some of the practice. You got about 3 practice problems of finding this information, and then we'll talk about some y-axis when we rotate around a vertical axis, or like the y-axis, and then we'll come back and we'll actually integrate these and solve to find our volumes.